ICID Central Office welcomes you all for the webinar on integrated water resources management and large river basins based on simulation modeling and optimization methods. We are very happy that the European Regional Working Group is taking up the organization of this very important webinar. We have Professor Dr. Ragab, President ICID, Dr. Irina Bondarik, our Vice President Honorary, and very eminent panelists, Mr. Buber Alexander, Dr. Buber Alina, and Dr. Buber Vladimir, who are all very eminent persons in their fields of simulation and modeling. And we feel that today's webinar will be a very, very important and a very useful webinar. So, next. President. So, वो जो था mute and question answer वगैरह वाला. Okay. So at the outset, I will request our President, Dr. Ragab, to provide the opening remarks, and then we start the rest of the proceedings.
Thank you, Secretary General, and thank you, Irina, for organizing that's a webinar. And I always really admire your capability on organizing so many events for ICID, whether it's in Moscow, Pittsburgh, on so many occasions. You never shied away from taking responsibilities for ICID. So I would like personally to thank you for all the efforts over the years for ICID. This subject actually is quite important because this is large scale basin management, and at large scale of basins, we always have different stakeholders. We always have different sectors with different requirements. Also, we have different activities from farming to fishing to tourism at such a scale. The integrated management is really important for planning at that scale, and usually requires the high level of government authorities to deal with the planning. And that planning is to avoid sub-basin conflicts. It is important to ensure good ecosystem services. It is also important to cope with the climate change and population growth. So for that reason, the integrated management of large basins is really very important. And I would really be quite happy to listen to the presentations today. I feel everyone will definitely benefit from the expertise and excellent scientists we have today. And by this, really, I would invite you to start your presentation. Thank you very much.
Thank you, President. Before we start the webinar formally, there are a few things we would like to work with. We will be having a separate question and answer session after the presentations are all over, and we would request you to send your questions in the chat box and keep them short and specific. And after the written questions, we will try to provide them to the presenters, and they may select the questions for answering. And if the time limit permits, then we may try to provide some of the other participants to share their experiences. And if you would like, and we have spare time, then kindly raise your hand so that then we can try to give you the opportunity. So I once again welcome all, and I would now request Vice President Honorary Dr. Irina Bondarik to take up the presentations as well as introduce the various other panelists. So, Dr. Irina.
Sure. I would say welcome for all participants. We are in the All Russian Institute for Hydraulic Engineering and Reclamation, and I would like to introduce our director, Mr. Shevchenko, who is the main person for the organizing activity and scientific research in our institute, and the panelist is the Dr. Buber, the head of the Department of Reclamation and Water Management Complex. The next slide, please. The Dr. Buber Alina Alexandrovna, the senior research of the Reclamation and Water Management Complex Department, and he is the main person for the simulation model in the MikeShare software and others for the rice growing. And the next slide. And Mr. Buber Vladimir Borisovich, he worked in VNIIGIM and participated in the development of mathematical models and algorithm for integrated water resource management for large river basins. And now I would like to get some welcome for our director, Mr. Shevchenko. Please. I will try to.
Уважаемые коллеги, добрый день. Мы рады вас приветствовать на сегодняшнем таком значимом для нас и, я думаю, для всех нас мероприятии.
Dear colleague, good day. I like to invite you to participate in our webinar.
Наш институт, старейший институт в России, поскольку через 2 года мы будем отмечать столетие нашего института. И наш институт как раз занимается вопросами управления водными ресурсами в бассейнах больших рек. Это бассейны реки Волга, бассейны реки Кубани, ну и так далее.
Our institute is the oldest land reclamation institute in our country. It's about 100 years, and one of the departments of our institute is connecting with the management, the water management for the large river basin, for the Volga River, for the Yenisei, and for the Kubani River.
Коллеги, и я уверен в том, что сегодняшний вебинар, он обогатит нас вот теми задачами, теми вопросами, которые сегодня остро стоят в повестке нашего мероприятия. И я надеюсь, что водные ресурсы, которые сейчас, так сказать, большие проблемы испытывают не только страны Центральной Азии, но и, наверное, большинство стран мира, это тот вопрос, который мы должны уделять самое главное внимание. И наша задача как специалистов должна быть именно в этом направлении и направлена. В этом направлении.
I hope that this webinar had been done the new knowledge for all of us about the development and management of the large river basin. This is the situation for all countries, and not only the Central Asia, but the other country. And we hope that we could discuss the approach for this for water management and have the good discussion now.
Еще раз я приветствую всех участников нашего вебинара, и я надеюсь, нам вот обстановка, которая возникла сейчас во всем мире с коронавирусной инфекцией, все-таки позволит нам как можно чаще встречаться не только в формате видеоконференции, но и в очном формате, поскольку очное общение – это весьма важно и продуктивно. Коллеги, приветствую вас и надеюсь, что сегодняшнее мероприятие будет весьма полезным и продуктивным. Спасибо за внимание.
We hope that the webinar in the online is not only the meetings in ICID, and hope that next year we can meet in real life and discuss this question during our meetings of ICID. Thank you. And now we begin our webinar in the integrated water resource management on large river basins. And I would like to say some words about the thematic of the webinar. When we think about trends on global water resource management, it's necessary to take into account that the agriculture sector of the economy is the most significant water user, consuming up to 70% of total volume of fresh water. This explains the reasons of the new vision of water problems by the International Commission on Irrigation and Drainage for the Future, and identify technical and institutional ways to improve water resource management, find consensus in existing contradiction, and promote compromise for sustainable solution. Integrated agriculture has the twofold impact on fresh water resource due to their intensive consumption and potential deterioration of the quality. The ability of irrigated lands to increase crop yield produced to somewhere 3 times the year provides the undeniable advantage of dry land farming. High performance and intensive technologies of irrigated agriculture have their drawbacks. Thus, over the past 50 years, imperfect irrigation methods have led to accumulate of soil in soils, their alkalinization and waterlogged on about 20% of area of all irrigated lands on the world. Agriculture has an impact on the climate.
Yeah, excuse me, Dr. Alina, your slides are not changing on the screen.
Yeah.
And kindly make it a full screen mode. We haven't been able to see the next slides, like, you know, what
Yes, but this is only the
Включите режим презентации и раскройте на весь экран.
And kindly make this a full screen mode so that people are able to appreciate the entire slide.
Okay. This is only introduction for
Yes.
the webinar, so I can.
Yeah, now it is perfect. Yeah, please.
Yes, I can say some words. As a result of specific problem of irrigation agriculture are the salinization, groundwater depletion, air, soil, and water pollution, and degradation of aquatic habitats. The research of the radical technology and innovation should be focused on adapting the practice and confirm economic of new and sustainable compromise between the incomes of the agricultural producers and the cost on environmental protection. The water resource management within a certain geographic region with waterworks and cascade of integrated reservoirs is a complicated problem how to use and share water between different branches of the national economy. The main principles of the management process are the systematic approach, stakeholder partnerships, accounting of the uncertainty of influence factors, basin geographic approach, and serious scientific support of reliable data. Based on the fundamental principles, it can be concluded that the methods of the water management are mainly determined by the using of computer technology as mathematical simulation models to solve practical problems. The basis methods.
Irina,
Yeah.
that we are still at the top slide. The slides
Yes,
didn't.
but this is the introduction of our one more words, and then we begin the slideshow. Okay.
Yeah, the slide they don't change, so we are still in the first.
Yes.
slide. Yeah.
Yes, but this is
That's okay. Okay.
okay. One way to solve the problem of integrated water management efficiently is implementation and development of mathematical models and use the results of operation service. All types of optimization model have a general concept. These models describe situation for many solutions that satisfy all limiters and find a set of the best decision. The selecting of optimization model should be based on the specific type of the application. For example, for formation of the best models for reservoir operation, it's need to take into account the interest of conflict of water use. At the same time, the quality of optimal water resource management is assessed by the statistical and multi-criteria analysis method. So now we want to present the research of this fundamental scientific field is being conducted in our institute. So the department of the land reclamation management complex is the main scientific department in our institute who work in this problem. The main goal of scientific justification of measures to improve the water management situation in the basins of large river. The following digital technologies are used as a tool: databases and geographic information system, hydrological forecast, making optimal management decision for water supply for agricultural facilities, and mathematical model and crop forecasting. And now we start with the first presentation. This is the creation of the geographic information system for reclamation complex for Lower Cuban Basin for integrated water management. The irrigated area on Cuban River Basin one of the largest water management complexes in Russia is developed in the Krasnodar region. The beginning of irrigation development and active reclamation construction in Krasnodar territory dates back to the beginning of the 20th century. Then the first hectares of irrigation were built and rice cultivation were carried out. This region is one of the largest territories of irrigated agriculture in Russia. This is about 385,000 hectares of rice crop rotation, and it includes 253,000 hectares of irrigated lands. Krasnodar region is the largest consumer of total and irrevocable water consumption by other districts of the Russian Federation. The water is distributed as follows: irrigation 90% and agricultural water supply 503%, and household and drinking needs about 0.1% only. The main river of the Krasnodar territory is Kuban. That's the next slide. The map of is relatively small, about 800 kilometers, but quite full flowing. Annual river flow is more than 12 billion cubic meters of water and incoming to the sea, while flow rate is extremely uneven. Currently, the water regime of Cuban Basin is greatly influenced by agriculture and also from the regulation of runoff and water intake for the needs of consumers. Reservoirs and canals were built during intensive land reclamation development in Soviet Union and regulate the Cuban River flow. We can see that there are about 54 reservoirs, 8,000 channels, and 300 pump stations, and about 1,000 dams. The Cuban is the main rice growing region of Russian Federation. You can see the dynamic of crop area change and dynamic of the harvesting of rice, about 1 million ton every year. This is the flooding of rice checks in the Cuban region. The main purpose for the geographic information system creation for Lower Cuban is the restoration and development of observation notebook, development of simulation mathematical models, development of rules for use of water resource for reservoirs, development of rules, programs, and action plan to in case of extreme low water, and integrated development of the system of state monitoring of water bodies. Where we could use this geographic system. It has been used for the hydrodynamic models of Lower Cuban in MIC 11 software package, simulation model for crop growing, water balance calculation for big territory, and development water use plans. The scheme of reclamation complex of Lower Cuban. This is the 11 irrigation system, 6 the rice growing irrigation system, are the cereals, and include the dams and channels and water works in this land reclamation complex. This is the scheme of the river network, and you can see the location of the main cascade of waterworks, consistent reservoirs, Krasnodar, Shapsut, Fedorovsky waterworks, Tikhovsky water driver, and 4th system for the rice growing, and the 2 systems below Tikharetsky water driving. So this is the very complicated task to sharing the water in this system. The composition of information support that we include to the big data. The reclamation systems, hydraulic structures, separately located hydraulic structures, indicator for the assessment and accounting of land reclamation status, data on human indicator of irrigation plan and structure of yields, and statistical report data for agricultural lands. The description of database is the state, it's named the state of the reclamation fund. This is platform, relational base. The access for the database is local and customer service, and 6 link tables. The database was created on the Seabase anywhere relation system. The system support both of local and client server database access options, and database contain the information of geographic information system as well. You can see the attributive tables and indicators of water works included to the database. The next. This is the main collection and analyzing information about main characteristic and for the channels. This is the 8 channels here. The large the reservoirs and dams in this region. This is 6 different reservoirs, 4 different reservoirs and 2 water works, Fedorovsky and Tikharetsky. And the main irrigation system in this region. This is the analytical reports that we can use after the the interconnection of tables makes it easy to obtain the comprehensive information and on any of the objects included to the database. You can see the analytical report fragments for the that we can have from the database that have been created for this territory. For actualization of the interactive detailed electronic information maps, it's geoinformatic system includes the collection, analysis, and storage and graphical visualization of spatial data with the possibility of editing them and include the shuttle radar topography mission, OpenStreetMap, and World Geographic System. On this slide is display input data, the space sentient material, administrative zone and location, transport system, territories of agriculture enterprises, location of reclamation system in the hydraulic structures for water intake and discharge, morphometric characteristic of riverbed and floodplain territory, meteorological and hydrological information, and hydrographic objects. And this is the some irrigation system with the characteristic and the irrigation area of the Timrukskaya irrigation system is about 700,000 hectares, in which 300,000 hectares are used for agricultural production. Water intake is carried out from the Cuban River and with annual volume about 0.2 million cubic kilometers. The Petrovska-Anastasevskaya rice irrigation system, the irrigation area is about 40,000 hectares, in which 37,000 hectares are used for agricultural production. Water intake is carried out from Kuban with the annual volume about 0.7 cubic kilometers. And Chernyakovskaya, Chernyakovskaya irrigation system. This is table for the annual volume of water, annual and efficiency of the interfarming network. And Mariana Chernogubolskaya irrigation system is the with characteristics. So you can see the conclusion of main application area of this system. The operation management of water resources, water supply and irrigation system, protection of territory from flooding, assessment of the reliability of the dikes of Lower Kuban, forecast of emergency, rules of joint regulation of reservoirs of the Lower Kuban based on the hydraulic models, the effect of artificially flooded area on the reduction of water level in floods, maximum permissible discharge to the download of the reservoirs of Lower Kuban for the passage of the flood wave without an accident, and determination of zone of possible flooding in the period of catastrophic floods, and passage of dam break wave during the hydrodynamic accident in the hydraulic structures, safety declaration. So this is some hydraulic notes in Krasnodar reservoirs, and thank you for the attention. This system is the base for the future future modeling of the dynamic of the reservoirs in the Lower Kuban. And the next presentation by Dr. Alina Bobin, serial research of our institute, is devoted for hydrodynamic modeling and multi-criteria analysis methods for the real-time water management in Lower Kuban Basin for agricultural purposes. So the next presentation by Alina Buber.
Hey, dear colleagues, greetings from scientists. Sorry, one moment, please.
Second, please, for presentation connection.
Oh. Good day, dear colleagues.
Could you see a presentation? Correctly.
Greeting from scientists of All Russian Scientific Research Institute of Hydraulic Engineering and Land Reclamation. I'd like to introduce your presentation, Problems of Water Resources Integrated Management in Kuban River Basin. Authors Buber Alina, Buber Alexander, Dobrachov Yuri, and Radkovich Evgeny. Next slide. Research goals and objectives. Calculation technology development on water resources management of the Lower Kuban Basin with agricultural lands reclamation in frequent low water conditions. Technology based on integrated use of 6 models developed in Russia: hydrological and meteorological forecast, simulation models of yield formation to calculate crop water demand, water balance models to develop water use schedules for irrigation system, hydrodynamic models to calculate water use scenarios, optimization model to choose a trade-off Pareto management options, and statistical models to calculate yield losses depending on water resources deficit. Next slide. The object of the research is irrigation systems that are hydraulically connected to a large specialized agricultural complex for rice production, located in the lower part of of the Cuban River basin and experiencing an acute shortage of water resource in the last decade. The area of irrigation system of the lower Cuban is about 300,000 hectares, of which no more than 135 hectares are wetted annually due to water scarcity. The annual rain-off of the Cuban River in this section line of the Krasnodarskaya Reservoir is about 14 cubic kilometers at 50% probability. The vegetation period from May to August accounts for about 50% of the annual rain-off. The main problems of rational use of water resources in the basin are associated with exceeding the maximum permissible withdrawal of water resources, administrative and department disunity in the operational of water industry facilities, lack of a reliable monitoring system, lack of legal and methodological document regulating water management and other activities related to the use of water resources. The coefficient water resources used in the Cuban River basin is 0.86. The value of irrevocable water consumption is 6.9 cubic kilometer against the normatively permissible withdrawal of 1.6 cubic kilometer. Water distribution is in the Cuban River basin is ensured by the operation of a system of hydraulic structure, including reservoirs, waterworks for various purposes, located in the riverbed and on tributaries, main canals. A system of distribution canals, water intake structure, and pumping station ensured the intake and transportation of water, industrial and agricultural enterprises. It is important to note that during the long period of operation of the water management complex of the lower Cuban, the operation characteristics of the hydraulic facilities significantly deviated from the design parameters, and management functions were removed from some structures. Krasnodarskaya Reservoir is designed for flood flow regulation and to provide water for rice irrigation systems. The available capacity of the Krasnodar Reservoir has significantly decreased due to siltation. Shapsukskaya Reservoir is designed for water supply and rice irrigation system. The Fedorovsky retaining waterwork is designed for the maintaining of suitable levels in the Cuban River for the purpose of water supply of irrigation system of left and the right banks of the lower Cuban. Tikhovsky water dividing waterwork is located in front of the section dividing the river into two branches, the Cuban branches and the Protoka branches, and provides water intake to Petrovsko-Anastasievska rice irrigation system. Kryukovskaya Reservoir is designed for flood control and irrigation for Kryukovskaya irrigation system. The Varnavinskaya Reservoir regulates the flood for 5 rivers and provides water supply of the Varnavinskaya irrigation system. The Protoka branch provides to needs of the Chernoyerkovskaya irrigation system, and Kuban branch provides Petrovsko-Anastasievskaya, Temryukskaya, and Azovskaya irrigation systems. The area of rice sowing of the past 10 years in the Krasnodar territory is 135,000 hectares. The yield on average in the regions has approached about 7 tons per hectare. The total amount of water supplied for rice irrigation together with reused water is about 2.5 cubic kilometers. The climate change is in recent years is aimed at increasing air temperature and reducing precipitation during vegetation period. The irrigation rate of rice on average reached 20,000 cubic meter per hectare. Due to frequent low water conditions, there is an acute water deficit for all water users. Next slide. As a result of the research, 6 computational technologies were developed. Model 1, hydrological and meteorological forecasts based on Hydrometeorological Center of Russia and retrospective data provide a meteorological and inflow data series formation for calculation months. Model 2, simulation models of yield formation provide evaporation and transpiration dynamics and crops water use schedules development. Model 3, water balance models of agro-landscape provide a water supply schedules development to inter-farm outlets and then water intake from the Cuban River basin to irrigation system. Model 4, hydrodynamic model for reservoirs and water work operation regime development. For each water use scenario, water deficit for irrigation system and reservoirs drawdown are determined and matrix of solution is constructed. Model 5, optimization model in Pareto front Weaver software, author lot of Alexander, Dorodnitsyn Computer Center. He is here today. Greetings and best wishes. Trade-off solution set is formulating and basing on decisions with water users. Optimal Pareto solution is accepted. Hydrotechnical structures operation regimes and determined by reverse scrolling method. Model 6, statistical models of yield losses. Yield losses depending on weather data, vegetation period, and water resource deficit for irrigation systems are calculated. During the vegetation period, calculation of water user schedule formation and reservoirs and water work operation modes is carried out monthly and clarified if necessary. At the end of the vegetation period, a water use schedule is formed for the next year by the year of 75% probability is terms of water consent and humidity. Next slide. For the model information support, the source data shown on the slide were used data of daily monitoring of water objects and irrigation system carried out by Special Reclamation and Water Management Organization and the Hydrometeorological Center. Maps of rice farms land use, water supply and drainage network schemes, soil maps and groundwater level maps, satellite and aerial photographs, digital elevation models, topographic and pilot maps. Next. Model 1, hydrological and meteorological forecasts for billion months based on Hydrometeorological Center of Russia data and retrospective data. Based on Hydrometeorological Center of Russia monthly inflow forecast for corresponding period, average inflow for forecast months and for period from the forecast months beginning till the forecast quarter end are determined. The database selects the year for which the observed inflow values for the particular periods are closest to the forecast values. Normalizing coefficients are calculated to adjust the forecast hydrograph. The forecast hydrograph of the selected year multiplied by the normalizing coefficient is taken as a model for calculation daily forecast values of inflows. A meteorological forecast is formed by the same algorithm. Model 2, simulation models of agricultural crops, yield formation, evaporation and transpiration from agricultural fields. Calculation was carried out using an original agrosenosis dynamic models development in our organization by my mentor, Professor Yuri Dobrachov. He is here today. I'd like to grade him too and wish all the best. Calculations were carried out from expenditure components of agro-landscape water balance described in the following model. Calculations were carried out for rice crops, corn, medium grown on irrigated massifs in rice paddy fields. Calculation of water consumption of cereal grass, corn, medic, spring and winter wheat were performed for non-rice irrigated and dry lands. Soil moisture is determined for the beginning of vegetation on planting data. According to the current and forecast meteorological data, the dynamics of evaporation and transpiration are calculated, and a crop water consumption schedules is formed. Evaporation and transpiration dynamics for vegetation periods shown on the graphs. Next slide. Model 3, agro-landscape water balance models. To calculate water balance dynamics of structurally heterogeneous territories, it is necessary to use mathematical models and algorithms with specially distributed parameters that allows displaying the process of geofiltration and mass transfer in porous media. For example, mud flow and mic shear. Such complex models require a large set of input data. An alternative is a simplified calculation using traditional hydrological methods for individual elements and layers. The entire area of the considered agricultural landscape is divided into separate parts by belonging of the category of lands and type of land use and surface water object. Agro-landscape rice irrigation system was divided on lengths of water objects, main and distributive canals, agricultural lands, rice irrigation systems, non-rice irrigated lands, and dry lands, human settlement lands, and natural phytocynosis lands, fields, and pastures. For each element of agro-landscape water balance components, calculations were performed by months of the vegetation period. Meteorological data were taken according to the meteorological forecasts model 1. And the rest of the series was modeling according to the year of 75 probability in terms of humidity. Evaporation and transpiration calculations were carried out using a dynamic models. Model 2, the agricultural crops variety corresponding to the structure of acreage adapted in farms. The water supplied to rice paddy field by inter and intra-farm canals was calculated, considering their lengths and degree of efficiency. Evaporation from water surface and coastal area, water volume, and priming at the beginning of vegetation period, as well as lateral outflow to neighboring elements. Water balance components adjustment was performed considering the relation with neighboring elements. According to SRTM data, a map of surface slopes was built. The lateral outflow is calculated depending on the ground elevation and the groundwater level of adjustment elements inside the site. The direction of water movement under the influence of gravity was estimated. Agro-landscape water balance calculation results were used for monthly water intake values for the Cuban River basin. It is important to note that water balance models can be used for water resource management analysis on rice irrigation system and justified action for their effective use by agricultural enterprises. Water supply schedule form for some branches compared with actual supplied water on 2018 year data shown on the slide. Water balance in the Kalininsky branch rice paddy fields with plan and actual water supply shown on the slide. Wetting demand non-fulfillment is observed in July, August, and September. It can lead to yield losses. The water use schedules formed in Model 3 are the requirements of water use for operation modes of hydraulic structure of the lower Cuban, which provides the required water level, science water intake to rice irrigation system is carried out from the Cuban River either in gravity modes through main canals or pumping station. It is also necessary to consider that the Krasnodarskoye Reservoir during the vegetation period should not be drawn down below the lowest operation level. Therefore, when developing the calculation scenario, 3 groups were drawn up with priorities for certain water users. Priority management for various rice irrigation system, priority management for the Krasnodarskoye Reservoir, for various releases, priority management for one rice irrigation system with a gravity mode of water supply from the Protoka branches located in the lower part of the basin. Water user R6. The slide shows the design scheme of water supply and the requirements of water users for the water management system of the lower Cuban. The design scenario is shown on the slide. Krasnodarskoye Reservoir management is carried out so that discharge in controlled cross-section will be 175 cubic meters per second or more. The Fedorovsky retaining waterwork management is carried out so to provide required water level on R1 and R2 and discharge values on R1 and R2 half less than required. Tikhovsky water dividing waterwork management is carried out so that discharge distribution ratio between branches Kubani and Protoka should be 40% to Protoka, 60% to Kuban. Other water users requirement R6, R7 considered by leftover principle. Matrix of solution, matrix of water distribution scenarios is shown on the slide. Next slide. Model 4, hydrodynamic model for the reservoirs and waterworks operating modes, formation in the interests of rice irrigation system. To form the reservoirs and waterwork operation modes during the vegetation period, a hydrodynamic model has been developed in the Mic 11 software using the control structure model. Using the control structure model allows you to assign water level and discharges according to the water user's requirement in controlled cross-section. And by iteration to select releases from hydraulic structure, which is important when assigning a strategy for the water management complex online. The gates level on structure is determined by the control strategy, which describes the function of gate level dependence on the value of water level and or discharge at the control point. The initial parameters for modeling are the priorities and requirements of water users set in the model shown on the previous slide. So during the vegetation period, for the gravity water supply to the lands of right bank and left bank massifs, the water level in the Fedorovsky waterwork upstream should be at least 13.4 meters. The control structure model based on PID algorithm iteratively select such releases for the Krasnodarskaya reservoir so that the level of the Fedorovsky retaining waterwork should be not below the 13.4 mark. The hydrodynamic model of the Cuban River was constructed from the Costa Hitagurov village to the mouth, the confluence of the Cuban and Protoka branches into the Azov Sea, considering the main hydraulic structure, reservoirs, tributaries, and water intakes, pumping station, and canals, which is designed to simulate the main hydrodynamic process in the river system. The total length is more than 1,000 kilometers. The boundary condition for water intake and water work were set according to the developed water use scenarios. The boundary condition for the inflow values using model 1. Model was calibrated on 7-string gauging station. The slide shows the model calibration results. The error was up to 5 centimeters. In the areas of the upper and middle Kuban, the model was not calibrated due to observation lag. Hydrodynamic model works adequately and can be used for scenario calculation. Calculation algorithm on hydrodynamic model to form a matrix of solution for each water distribution scenario is shown on the slide. Based on water use schedules formed in previous 3 models and water users requirement error high, different water distribution scenarios showed on previous slide are determined. Source data is formed for each scenario and hydrodynamic modeling using a control structure model is performed. The slide shows calculation results. The level fluctuation at water intakes R4 and R6 for 2 alternative scenarios. Blue is favor of R6, black is favor of R4, red requirements. Water deficit values for water users are determined for each scenario as well as reservoirs drawdown. Based on the water users' schedules developed in the previous model, the volumes of water withdrawal during the vegetation period for each water intakes are formed. The deficit or probability for the water users is calculated in percent during the growing season. For reservoirs, the percent of drawdown is determined by formula shown on the slide. Matrix of solution based on calculated deficit and reservoirs drawdown is shown on the slide. The table contains the values of deficit for all water users. The average and the total deficit are calculated. Model 5, multi-criteria analysis of the calculation results. For the obtaining matrix of solution, curves of Pareto boundaries were formed by method of multi-criteria analysis based on the method of achievable goals, which should be used in the process of discussion between decision maker, Cuban Basin Water Management Department, and interest water users, the directorates of reservoirs and water works, the Cuban Management Department, and water users Department of Reclamation System Management, directly subordinate to him, to choose the optimal in the sense of Edgeworth-Pareto trade-off solution. A computer expert support team also takes part in the discussion and prepares several initial trade-off scenarios and accompanies the decision-making processes. Visualization of the results of calculation in the process of making an optimal decision is performed on the Pareto Front-Weaver software, which implements the method of achievable goals. Scenario 149 is which the discharge from the Krasnodarskaya Reservoir was 65%, the average deficit was 26%, and the total deficit was 7%. The lowest is shown on the slide. The deficit for other water users is shown on the slide. Next. Scenario 150, in which the discharge from the Krasnodarskaya Reservoir was 96%, maximum close to the lowest operation water level. The average deficit was 15%, the lowest, and the total deficit was 7% minimum, is shown on the slide. The deficit values for other water users are shown on the slide. Next. Scenario 69, adapted during the conversation of the decision-making person with interest water users. The discharge from the Krasnodarskaya Reservoir was 40%, the average deficit was 29%, and the total deficit was 20%. The deficit values for other water users are shown on the slide. The argument for the adoption of this scenario was the work of a small shipping in the Krasnodarskaya Reservoir water area. To reflect the economic components of the purpose of a particular water management strategy, a technology for calculation crop losses depending on the short-range water supply and current meteorological conditions is proposed. A statistical model based on productional data for the last 10 years has been developed, which makes it possible to assess the impact of reduced water supply on yield depending on the vegetation phase and meteorological condition. The approach makes it possible to evaluate crop losses depending on water supply deficit for irrigation systems. The need to develop such a technology is justified by the fact that at the end of July of 2020, there was an extremely unfavorable hydrological situation caused by low inflow of the Krasnodarskaya Reservoir and lack of precipitation. The reservoir operation was in zone of reduced water yield. It was necessary to reduce the irrigation water intake by the main structure of rice irrigation system. It turned out to be impossible to provide working horizon in the Kuban River for water intake, which lead to reduce of water supply during the rice tillering period in several districts. By the first decade of August, the Krasnodarskaya reservoir reached the lowest operation level. The irrigation rate of rice in 2020 was 17.6 thousand cubic meters per hectare, which is lower than the long-term average by 2,000 cubic meters per hectare. However, a decrease in the wetting rate at the end of the vegetation period did not lead to significant crop losses. The necessity of assessing crop losses depending on the shortage of water resources, in particular with vegetation phases, is relieved. The percentage of rice yield losses in each scenario was calculated based on the difference between the actual irrigation rate volume and the calculation volumes, based on the results of hydrodynamic model correlated to the actual area of rice irrigation. The slide shows a fragment of the crop losses calculation depending on the shortage of water supply for various scenarios. The technology allows The technology allows adapting optimal trade-off solution online with the lower Kuban water resource management in interest of agriculture. Water supply of rice irrigation system is conditions of water scarcity is a complex task that requires improving the management of the entire structure of water use and irrigation technologies. The solution of this problem in the direction of both the search for new sources of water and its most rational use is impossible without the use of the least digital technologies and mathematical modeling. On the basis of the development computing technologies by methods of multi-criteria optimization analysis, decision makers are provided which technically justified options for trade-off solutions. Now there is step-by-step implementation of our models and developments in the rice agro complex of the Lower Kuban. We thank the administration of Kuban Meliot Coast Management Department, Frolov Boris and Yakuba Sergey for kind cooperation, providing initial database and assistance in conduction expeditionary research. They are here today. Greetings and best regards. The accumulated world experience of efficient use of water resources in agriculture is reflected in the publication in Irrigation and Drainage Journal, which makes our work more productive and allows us to reduce the routine part of scientific research. We thank the International Commission on Irrigation and Drainage for providing this conference, and I'd like to show you a decision process between this decision maker and water users in Pareto Front Weaver software. I will ask Evgeny Radkovich, junior research, to help me, please.
Okay. So, can you hear me?
Yes.
Yes, we can hear.
Just a second, please, for the screen demonstration. So, can you see a program on your screen?
Ира, ты после этого спроси вопросы.
Okay, so that's a little addition to the previous report. So as mentioned in the previous presentation, for each water users, based on hydrodynamic modeling results, a matrix of solutions transformed into deficit values. So in Pareto front viewer, as well as in database file, you can see this matrix for a number of different scenarios. So Pareto front viewer is using for multi-criteria analysis and to visualize these solutions and to choose trade-off Pareto solution during conversation between water users and decision-making person. So the first step is uploading the matrix of values. So you can see these values here. So we have a different number of scenarios. It's about 150 scenarios here. So the next step is visualize settings. Visualize settings. So in this setting, you can assign a particular parameter or criteria to axes OX and OY and to color set X. On color X, there is usually a criteria water user, which is on top of water users requirements hierarchy, whose requirements should be considered first. For example, we'll set QX values as average deficit value, OY as a summary deficit value, and on color set, we'll take a Krasnodarskaya reservoir as a top water user in the hierarchy, okay? So after these settings, we can see the whole solution matrix. And by considering a management experience, hydrological situation, and etc., a decision-making person chooses a first point in the whole matrix of solutions. He says, for example, that average deficit should be between 30 and 40, and maximum deficit value should be between 14 and 16, and he picks up the first point. So in each matrix point, you can see deficit values for all users related to the point. So depending on these values, each water user forms its requirements. For example, in the chosen point, you can see that the top hierarchy user, Krasnodarskaya reservoir, they can say that that 46% deficit is too much for them. So decision maker sets a suitable color criteria for this top user between 30 and 40. So now, based on deficit values for the top criteria, decision maker person sets another deficit values of another water users by moving the scroll bar connected with each user by changing the deficit value for them. So you see the matrix change its view, and then is picking a point again. So now the deficit for Krasnodarskaya reservoir is 40%. But it could not be enough still after that. So of course, because other water users can say that that situation is not suitable for them for some reasons. So the scroll bar moving repeats again and again and again until finding an optimal solution for all water users. So that's a small illustration how a decision-making process looks. Thank you for your attention. Okay, and now, if you don't mind, let me please continue our webinar by next report, reported by Alexander Buber and Evgeny Radkovich. Please, just 1 second for presentation screen. Can you see the presentation in the full screen mode? Okay. Okay, dear webinar organizer, dear colleagues, allow us to present modern approaches, methods, and tools for an integrated water resources management in large river basins. Methods for constructing the best release rules that ensure the safe operation of facilities and the sustainable functioning of water management systems will be considered. The construction of optimal trade-off release rules is based on the methods of multi-criteria analysis and the trade-offs theory, and should consider the often conflicting requirements of water users. To assess the quality of release rules, statistical reliability criteria are used, which are formed as a result of performing water resource calculations for long-term hydrological series of observed inflow. In the basins of large rivers with a large number of river hydropower reservoirs, it's necessary, on one hand, to make operating decisions on the interconnected passage of flood through waterworks. On the other hand, to ensure guaranteed water supply to all water consumers and users during the low water period. At the same time, considering the forecast and actual inflow to the reservoirs cascade, it's necessary to meet the following water management system participants' requirements to the discharge and water levels. Not to allow levels in reservoir be forced above the flood control level until the capacity of the spillways is completely exhausted. When carrying out different activities, maintain the limiting levels of water filling in reservoirs to prevent releases into the downstream reservoir, leading to damage from flooding of developed floodplain lands.
The slides are not changing really. We are still at the first slide. We didn't really see the second or third slide yet.
Okay, we'll try to fix it again, sorry. Some technical problem. Can you see that?
Yeah.
That's why they're changing, huh?
Yeah, that's fine. Yeah.
So ensure energy releasing volumes determined by the rules. So, and meet the requirements of water users, energy, navigation, municipal engineering, ecology, agriculture, fisheries, and others in the amounts determined by the rules. Maintain fishery releases during the spawning period while preventing even short-term drops in reservoirs water level. Maintain agricultural releases during the growing season from April to September. Provide water users with consistent reliability. A typical example of an object requiring the solution of such a problem is the Amgarsky cascade of reservoirs, including the Lake Baikal, Irkutsk, Bratsk, Ust-Ilimsk, and Boguchansk hydropower plants. As an example, we'll use a water management system that includes Lake Baikal and the Irkutsk reservoir. In many cases, both in dry periods and high floods, there is no unambiguous regulation schedule, and it's necessary to make a decision from several compromise options, in each of which the requirements of certain participants in the water management system are violated. In Russia, in modern operational practice, such decisions are usually made on the basis of dispatch control schedules developed on the basis of long-term hydrological series and the experience of managing water resources in the basin in previous years. However, as practice shows, the use of optimization methods when performing water resource calculation for a long-term historical series of inflows gives significantly better indicators of control reliability than dispatch schedules. So the purpose of the webinar is to demonstrate and discuss computational technologies that allow you to design both dispatch schedules and release rules based on optimization methods and the trade-off theory. In Russia, requirement documents have been adopted on the development of reservoir water resources use rules, which define the requirements for the construction of release rules based on dispatch schedules. So formulate the procedure for regulating reservoirs according to dispatch schedules and provide criteria for assessing their reliability. The dispatch schedule established the flow regulating rules for the reservoir, allowing to determine the releases from the reservoir depending on the level or volume for water and the period of the year, decade, month. In the general case, the dispatch schedule is a set of piecewise linear functions, interruption lines, sorted in the descending order and defined on a discrete set of time periods, decade, month. For each zone, between two adjacent interruption lines, the range of the levels and the water discharges allowed for this zone is set. We can see them on the next slides. Feature 1 and feature 2 are shown on the following slides. So here they are. So this slide shows fragments of the dispatch schedules, coordinate table, and long-term series of inflow to the Lake Baikal. Principles of reservoir operation mode control, direct and reverse. First, the water level at the dam at the end of the estimated time period is determined by the level at the beginning of the period, the forecast inflow, and the range of acceptable releases for the zone in which the level was located at the beginning of the period. The second one, the water level at the dam at the end of the estimated period is determined by the level at the beginning of the period, the forecast inflow, and the range of allowable releases for the zone in which the level will be at the end of the period. So the slide shows two operation mode control options. In the first one, the releases range is taken from zone M+1, in the second for zone M. You can see these ranges on the slide for M+1 and M zone. In the Excel environment, on the Visual Basic Language, a program for performing water resource calculations for the Amgarsky Reservoirs Cascade was developed using long-term inflow series based on the specified coordinates of dispatch schedules. The slide shows balance equation for T+1 period. Reservoir volume in the next time interval is equal to reservoir volume in the current interval plus inflow and minus release. When performing water resource calculations, the following data are formed and used. First, start dates of periods, volumes in the Lake Baikal at the beginning of the period, useful volume of inflow to Lake Baikal by periods, dispatch schedule of the complex Lake Baikal-Irkutsk reservoir, releases from the Irkutsk reservoir by periods. The Irkutsk reservoir level depends on the level of the Lake Baikal and the release according to the corresponding dispatch schedule. Downstream level of the Irkutsk reservoir is calculated based on the existing level release curve. For the Irkutsk hydropower plant, the head is calculated as the difference between upstream and downstream level. Turbine discharge and power are determined by the operational characteristics of the hydropower plant. The main indicator of the management reliability by dispatch schedules is the calculated probability of water yield, providing the consumer with water, expressed as a percentage of uninterrupted years, months, decades for the entire estimated reservoir operation period. The reliability is determined on the basis of a statistical processing of water resource calculation results performed for a long-term series of observed inflow. The reliability of each water user requirement is calculated by the formula shown on the slide. So in this formula, M is the number of calculation periods in which the water user's requirements was not violated. N is the total number of calculation periods in the long-term hydrological series. When developing release rules, it's necessary to determine such a configuration of dispatching schedule, which will provide for each water user the following standard reliability of normal water consumption by the number of non-violated years. Sanitary releases, 97–99%. Water supply, drinking, household, industrial, 95–99%. Hydropower, 85–95%. Navigation with maintaining water levels by releases from reservoirs, 85–19%, 90%. Irrigation and agricultural watering, 75–90%. Fisheries, 75–90%. Due to the fact that the indicator of reliability of ensuring guaranteed water yield by the number of uninterrupted years does not allow determining the depth and duration of an intra-annual distribution of water deficit, a reduced reservoir yield is introduced into the regulation regime by 10, 20, and 30% of the guaranteed amount. The reliability of the reduced yield sets significantly higher than the reliability of the guaranteed reservoirs yield. Designing a dispatch schedule is a complex process. It's difficult to assess the dispatch schedule management effectiveness. The dispatch schedule management quality essentially depends on water users' requirements priorities hierarchy, expressed in reliability criteria. If all water users' requirements are satisfied with the normative reliability, then the dispatch schedule can be put into operation. However, if water users' requirements of water users conflict and the water resource calculations on dispatch schedule does not give the normative results in reliability terms, then it's necessary to find such a configuration of dispatch schedule that increases the water users' reliability requirements values depending on their priorities. At the same time, the dispatch schedule developer always had three problems. First, are the dispatch schedule's parameters, coordinates, well chosen? It asks, a valid dispatch schedule solution exists, but developer has not found it. The second, how well are water users' requirements being met in the adopted hierarchy? Is it possible to select the dispatch schedule parameters so as to improve the reliability indicators for conflicting requirements? The third, is the dispatch schedule management optimal, or is this possible to achieve better results using other management tools? Does the reservoir water capacity of the catchment area allow it to satisfy the water users' requirements? So the first two problems are solved on the basis of methods for finding the optimal coordinates of dispatch schedule. Although a complex nonlinear discrete piecewise continuous optimization problem of small dimension, in our case 168 independent variables, arises. Its solution requires great skill and special optimization methods. The authors use special methods of local optimization and genetic algorithms. These methods do not give a global optimum, but they significantly improve the reliability indicators of water supply to users. The third problem is related to the solution of a rather complex optimization problem of large dimension. In our case, it's 1056 independent variables. which requires the development of special optimization methods, since it's almost impossible to solve an optimization task of such dimension in a reasonable time using nonlinear programming methods. However, only its solution gives or refutes confidence in the quality release rules. The meaningful formation of the optimization task is as follows. It's necessary to determine the releases, independent variables, from the reservoir for the entire calculation period, which minimize a certain objective function under constraints associated with the fulfillment of balance equations. The objective function is calculated depending on water user's requirements and should decrease with decreasing failure events when required releases violate the threshold. Water user's requirements priorities hierarchy is reflected in the objective functions by values of penalty coefficients. The higher priority, the higher penalty for requirements violation. The initial data for the optimization task is the interval inflow series, initial and final reservoir volumes. So the next report is devoted to different approaches to building release rules based on dispatch control schedules, which are adopted by regulatory documents in Russia. The second report is devoted to the construction of release rules based on optimization methods and the trade-offs theory. Some definitions are repeated in the reports for better understanding. Thank you for your attention. Vladimir Borisovich Buber is the next reporter. So if you don't mind, I'll give him a word. Vladimir Borisovich, please continue our session. Vladimir Borisovich. У вас микрофон.
Да, thank you. Now, just a minute, I will to connect. Okay, can you see my screen?
Yes, thank you.
Okay. Good afternoon, colleagues. Thank you for opportunity to discuss the problems on this webinar. In this work, we present an attempt to improve the quality of water resources management according to the spot schedules on the case of the Lake Baikal-Irkutsk Reservoir complex management. At the previous presentation, many words was said about dispatcher schedules, so I can only say that the dispatcher table contains the sum of the nodal points between in interval boundaries and for each zone between two adjacent nodal points at the same interval boundary, the range of permissible water flow discharge rates are set. The points of this dispatcher form piecewise linear curves ordered by levels. The quality of the design dispatch schedule of the Lake Baikal-Irkutsk Reservoir complex was determined on the basis of the water resources management calculations for a long-term hydrological inflow series using water balance equation. Here is W is reservoir volumes at the beginning and the end of each interval. Q is inflow and R is discharge volumes during the interval. As a result of calculations, the number of violation years was calculated for each water user mentioned in the previous report. The violation year is the year with at least one deviation for the water user's requirement. As a rule, it is impossible to fulfill all user requirements simultaneously. Thus, a conflict of interests arises, and it is necessary to build one or more compromised dispatch schedules agreed with water users. To build a compromised dispatch schedule, it is possible to operate as follows. Suppose there is a number of water user requirements that must be satisfied in the management process. Let the number is equal to K. Sorry. Let Vk be the number of violation years for the case requirement, Pk be the penalty coefficient with which determines the place of case requirement in the priority of water user requirement hierarchy. The larger the P coefficient value, the more significant is the requirement. The penalty objective function Fk for case requirement violation can be defined as Fk is equal to Vk multiplied by Pk. The total for all requirements penalty objective function F then may be the sum of all Fk. The F value can serve as an assessment of dispatching management quality. The lower value of F, the higher is the quality of the dispatcher for the used penalty coefficients set. Thus, the problem can be formulated as follows. To find the dispatcher nodal point configuration for which object function has a minimum for the given set of the penalty coefficients. Dispatcher optimization can be performed by searching for new positions of dispatcher nodal points on the boundaries of intervals. The nodal points of ice line and the case interval can be shifted upward to the I-1 line direction or downward to the I+1 dispatcher line direction, upward or downward. For upward shifting, new point coordinate can be calculated as linear combination of Zi-1 and Zi coordinates. For downward shifting, is linear combination of Zi and Zi+1 coordinates. In both cases, shifting parameter alpha takes value between 0 and 1. If 0, there is no displacement. If 1, there is a complete displacement to the adjacent point up or down, respectively. The golden ratio method was used to find the values A alpha asterisk and alpha double asterisk that minimize F asterisk when the nodal point of this is shifting upward, and F double asterisk when the nodal point is shifting downward, respectively. Among the A asterisk and A double asterisk value, the one for which the value of F is less is selected. It defines a new nodal point position, Zi, which minimizes the objective function value. We use two types of dispatcher optimization algorithms. The first one is vertical or V algorithm. The second is the horizontal or H algorithm. When vertical, calculation of the nodal points' optimal position are performed sequentially for all intervals boundaries at each border simultaneously for all lines. Thus, the nodal points for two adjacent interval boundaries can be shifted in different directions. The self-similarity of the dispatcher's line may not be preserved. When horizontal calculation are performed sequentially for all lines, at each line simultaneously for all points. All nodal points of the same line are shifting in the same direction. Some kind of the self-similarity of the dispatcher's line is preserved. In both cases, the nodal points coordinates of the first upper and the last lower lines remain unchanged. These lines hold their positions. The combined optimization algorithm involves the alternate use of vertical and horizontal algorithms. Both can be applied an arbitrary number of times in an arbitrary order. In this case, the result of the calculation at the previous step are transmitted as source data for the subsequent calculations. As an example, the effect of optimization of the objective function and dispatcher configuration for HV and VH optimization is shown on this slide. In both cases, horizontal optimization leads to a larger decrease in the objective function. On the dispatcher plots, the solid line without markers corresponds to the initial configuration. The solid line with round markers corresponds to the horizontal optimization, and the dashed line with square markers corresponds to the vertical optimization. These two tables shows the change in the management quality according to 11 criteria for various optimization options for the 114 years of hydrological series from 1903 to 2016. In both tables, the green background corresponds to an improvement, and the purple background corresponds to a worsening of the situation compared to the original dispatcher. The first table shows the change in the number of violation years. The first three rows of the table show criterion numbers, penalty coefficients values, and the number of violation years for the original dispatcher, the last one on a yellow background. The next four lines containing data on the number of violation years after optimization. Criteria 6 and 9 related to water supply have been the highest priority. During the optimization, it was possible to reduce the number of violations by this criteria to 0. The next group of 5 criteria, 4, 5, 7, and 8, 7, 8, and 10, have the next lower priority level. For this group, a decrease in violation was obtained in 9 cases out of 20. In 4 cases, the number of violations was not changed, and in another 7 cases, it increased. For the 4 remaining criteria with lower priorities, these values are 15, 0, 5 respectively. Another one indicator used for the management quality assessment was the violation depth value. This is the largest deviation of criterion value for the from the requirements of water users in the entire hydrological series. The change of the depth of violations as a result of optimization is shown in table 2. The last 3 lines in both tables show the effect of penalty factor value for criterion 4 on optimization results. It can be seen that with an increase in the penalty, the number of violations for the criterion can be reduced to 0. Of course, by worsening situation for other criteria. The obtained results allow us to conclude that with the proposed method, it could be possible to obtain the various dispatch schedules for finding compromise solutions, taking in account the requirements of various water users in the case of water resource shortage. Thank you all for your attention, and I'm finished.
Okay, thank you, Vladimir Borisovich. So, dear colleagues, if you don't mind, I will continue the next report. The last report. Finally. Okay. So, one more time, second.
आगे से ना ये थोड़ा सा वेबिनार में नंबर ऑफ पैनलिस्ट कम करवाने पड़ेंगे। हाँ, पैनलिस्ट डिस्कशन के लिए आ सकते हैं, पर प्रेजेंटेशन
Здравствуй, да? Да. По-моему, да.
Anna.
Да, Анна.
Okay. Can you see a presentation on full screen? Is it changes?
That looks fine.
Okay. So, last report is real-time water resource management using optimization methods and multi-criteria analysis for Lake Baikal Irkutsk Reservoir case study. Climate change assessment in recent years, development of computational technology for performing optimal water resources calculations, comparison of the release rules reliability using dispatch schedules and optimization methods. Integral reliability indicators are proposed. Release rules development based on optimization methods. Practical justification of the proposed release rules. The Lake Baikal Irkutsk Reservoir complex release rules are being considered again. The Irkutsk Dam is used to regulate the level of Baikal Lake. Baikal, as you know, is the largest freshwater lake in the world, containing more than 20% of the world's fresh surface water. The main task of constructing the rules for the reservoir's water management is the development of a release rules.
So the release rules reliability is determined on the basis of a statistical analysis of water resource calculations based on long-term hydrological inflow series to reservoir. In Russia, it's legally accepted that reservoir water management is carried out using dispatch schedules. As previously mentioned, in Russia, reliability is determined by the number of uninterrupted years. Due to climate change, dispatch schedules quickly lose their reliability. The mathematical model of finding releases to the Irkutsk reservoir downstream task for a given long-term inflow series is based on solving a system of interval balance equations. The main dependent variables are calculated using the known functions for the Lake Baikal Irkutsk reservoir. Bathygraphic function, Lake Baikal level and volume, Irkutsk reservoir upstream level depending on Lake Baikal level and releases. Downstream level depends on Irkutsk reservoir release, and hydroelectric power depends on headwater and tailwater levels and release. The main criteria are navigation release should be more than 1,500 cubic meters per second. Flood control release should be less than 3,200 cubic meters per second. Hydroelectric power should be more than 347 megawatt. The Lake Baikal level on May 1st for fishery should be 456.15 meters. For assessed climate change, 2 periods of 44 years of historical inflow time series were taken from 1932 to 1976, on which the dispatch schedules were built, and from 1976 to 2020. In addition, the 2 44-year series were modeled with the average parameters of inflow and the low water series. For these 4 series, water resource calculations were carried out using dispatch schedules. Calculations have shown the genesis of climate change. On the basis of multi-criteria analysis by statistical criteria, it was shown that the operating dispatch schedules does not provide control with normative reliability in recent years and in the low water period. The analysis showed, first, dispatch schedules must be developed on historical hydrological series over the past 20-30 years, and not on the entire series. The second, dispatch schedules must be updated every 10-15 years. So, as mentioned before, designing the dispatch schedule is a complex process. If all water users' requirements are satisfied with the normative reliability, then it can be put into operation. However, if it does not give normative reliability, the developer has problems. Other dispatch schedules coordinates well chosen, valid dispatch schedule solution exists, the developer hasn't found it. How well are water users' requirements being met in the adopted hierarchy? Does the reservoir water capacity of the catchment area allow is to satisfy the water users' requirements? Is the dispatch schedule management optimal, or is this possible to achieve better results using other management tools? The first 2 problems are solved on the basis of methods for finding the optimal coordinates of dispatch schedules. The author have developed such a toolkit for Lake Baikal. The third problem is related to the solution of a rather complex optimization problem of a large dimension, which requires the development of special optimization methods. The slide shows the author's algorithm for solving the third problem, called Pulsating Spring method. The formulation of the optimization task is necessary to determine the releases from the reservoir for entire calculation period, which minimize a certain objective function under constraints associated with the fulfillment of balance equations. The iterative algorithm for finding the optimal solution is as follows. Using the dispatch schedules, we find the initial solution. Outpass the volume values in the first and last interval of a not 2 year, 1/3, 5th, etc. are fixed, and Solver Excel solves the task of minimizing the objective function of the corresponding 2 year. Even pass the volume values in the first and last interval of an even 2 year, 2nd, 4th, 6th, etc. are fixed, and solver axle solves the task of minimizing the objective function of the corresponding year. The second and third iteration are repeated until the convergence of the objective function is achieved. Thus, the original large dimensionality optimization task is split into optimization of 2-year subtasks that can be solved independently of each other. This decomposition makes it possible to use multitasking and multiprocessor computer modes. Such an algorithm was implemented in Excel using the Visual Basic. Feature shows the step-by-step changing of objective function as a result of calculating the 4 cycles of even and odd passes. Water resource calculations have been performed based on optimization. Comparison of statistical values of reliability of calculations for dispatch schedules and optimization shows that for the 1932-1976 inflow, the reliability under optimization increases in criteria 3, 4, 7, 9, and 10, and decreases in criterion 2, and practically does not deteriorate for all other criteria, since the dispatch schedules is built for the 1932 and 1976 inflow, there is no significant improvement in reliability. However, for the low water series 1976-2020, in almost all criteria, there is a significant improvement in the reliability due to the poor work of the dispatch schedules. The obtained values of reliability during optimization almost completely fit into the normative ones. This shows that even in a dry season, it's possible to management with normative reliability if construct release rules close to the optimal. Statistical performance criteria, reliability, resilience, vulnerability, make it possible to quantify the reliability of using the adopted release rule for each individual water user's requirements. Unfortunately, the objective functions also give a poor representation of the quality and total impact of the release rules on the comprehensive fulfillment of water users' requirements. For a multi-criteria analysis of a criteria set, an integrated normalized reliability index is proposed. It's defined as the sum of failure for all criteria divided by the number of years in the time series. The table shows how the optimization improves reliability in comparison with dispatch schedules and with normative reliability, last row. Calculations have shown that optimization forms more reliable release rules. The authors have developed the computational technology that will make it possible to manage the reservoir water resources in an operational mode on the basis of optimization methods and inflow forecast. It's implemented in the Microsoft Excel using the optimizer described above. This technology forms releases for the next time interval depending on the reservoir volume and the interval beginning. Hydrological inflow forecasts for this interval, historical inflow series, and the actual water users requirements for this period. The slide shows the flowchart of algorithm. At the beginning of the year formation of the long-term forecast inflow, replacement of forecast inflow for the current interval by the value of the short-term forecast, determination actual water users requirements, formation and solving of the optimization task. The optimal release for the current calculated interval is taken as the regime for the maintenance surface. At the end of the current calculated interval, the real release and inflow are used to determine the final volume of the reservoir. The algorithm is mathematically rigorously stated in the article on the slide. Let P is the historical inflow series with the length duration of T years. It's necessary to make a decision on the reservoir operating modes in the current T plus 1th year. The variability of climate is controlled by natural processes such as ocean cycles, changes in solar activity, volcanic activity, and anthropogenic factors. The largest contribution comes from solar activity, which has been documented by a large body of published case studies. For a long-term multi-year forecast, The authors recommended to use 11 last years, since precipitation correlates quite well with the 11-year solar cycle of Schwabe. The slide shows the algorithm for generating the forecast inflow series. Last 11-year array alpha in the initial hydrological series P is allocated. We find below alpha the 11-year array beta in the initial hydrological series P close to alpha in the accepted measure. The proximity measure can be determined as the sum of the absolute values difference elements of the arrays alpha and beta. Let gamma be the array separating alpha and beta. The series P1 equal to gamma plus alpha will be used for calculating releases by optimization method. The performed statistical analysis of the 11-year cyclicity of the historical hydrological series of inflow showed that there is a weak 24-year cyclicity. The slide shows the autocorrelation function for the relative difference curve. In practical work, 11-year series forecasts were used without gamma. An experimental proof of the developed approach correctness was carried out for an 11-year historical series, 1914-1924. The calculations were performed according to dispatch schedules, optimization along the entire series, and optimization according to the proposed algorithm. The expected result is obtained. The reliability according to the proposed algorithm is higher than dispatch schedules, but of course worse than optimizing for the entire series. Statistical analysis of the results by integrated normalized reliability index confirmed the quality of the proposed computational technology. Unfortunately, it's impossible to rigorously prove mathematically that the proposed algorithm gives better control than dispatch schedules for any reservoirs. So, in conclusion, water resource calculations based on optimization methods give results in terms of reliability much better than when using dispatch schedules. Developed computer technologies for the formation of the reservoir optimal trade-off operation modes and presented practical proof of its effectiveness. For the implementation of the computer technology, a unique optimization algorithm for water resource calculations was developed that allows for quick solving of complex nonlinear tasks of large dimensions. Thank you for your attention. We try to answer all your questions in the chat. Thank you.
Thank you very much. Okay. I would like to thank our panelists who had the presentation in this webinar. We show you the main approach for the water management elaborated in our institute in our country, and I hope that it's will be interested for all participants, and we are open for the cooperation for the next discussion. Now we answer for the question in the chat. There are some questions there, and we answer for this. So I think that we could close our webinar, and once more, thank you very much.
Before you close,
yes,
I have really few questions. Maybe some participants didn't write it, but I have some questions for the panel for discussion.
Okay.
My first question is that how the climate change, especially extreme events like stream and droughts, extreme flood and droughts, were taken into the calculation of reliability, the annual reliability of the reservoir. That's question number one. There was really figures shown about the percentage of reliability versus time at different periods. And it didn't really show much how the rainfall, would it change with time? And how the crop water requirements will also change with time, because for ICID, we pay more attention to the crop water requirements and irrigation requirements. I didn't really see a graph showing the change in the irrigation requirement over time in relation to the climate change. The other important question as well is that in the presentation about the violation years of the reservoirs, I don't really know who actually is in control of the water. Is it the user? Who violates actually the rules? Is it the water user or someone else? Because my assumption is that if the water is controlled, water distribution is controlled by the water authority, then the user cannot violate the rules. And that's really the case in some countries. The water distribution is very much governed and controlled by the authority. So there's no chance for the user to take more water than he or she is allowed. So that's really another question. Also, some other questions related to the cascading reservoirs. The cascading reservoir system in Angara River, would that allow different withdrawal rates from different reservoirs? Would the system cope with different withdrawal rates from different reservoirs? And so, and also, let me have another question raised by one participant. He was talking about how it is possible to have efficiency, water use efficiency, and inter-farm efficiency equal to 1. How did you manage to come to that high efficiency? And also, that's from me. When I use hydrological models myself, I use a goodness of fit criteria. I commonly use Nash-Sutcliffe as a coefficient for goodness of fit. In your hydrological models, I don't know really what criteria you actually are using to say the calibration or the validation was acceptable. And also the multi-criteria analysis was showing some trade-offs, and what actually it didn't really explain what the trade-off between what and what. Do I trade off some water for agriculture to give more water to tourism? What exactly the trade-off in the multi-criteria analysis here? So that's really enough for me for now, and I will leave you to have some fruitful discussion for the rest of the time. Thank you.
Читай вопрос по-русски.
По одному. Could you please formulate question one by one, please? Because there's a lot of questions just in one phrase. We heard something, but
would you like me to say them again?
Yes,
no,
one question.
Just maybe separate them. Some kind of.
One first question.
Okay, let us go to the hydrological models first. The hydrological models, that when you calibrate a model, then you calibrate that model and based on some criteria, and we use as a goodness of fit criteria equation is called Nash-Sutcliffe efficiency. And in the calibration of hydrological models, there was no mention on what's the goodness of fit criteria used to say the calibration was okay and acceptable.
Какому это докладу? Вопрос.
For which report is it? For agricultural model of the river Cuban? Yeah.
No, it was for the hydrodynamic model.
Гидродинамический.
Калибровка. У нас
Спрашивают,
были
как
наблюденные данные по гидропостам, по которым производилась калибровка, были значения QH, да, в нижних вверх. Наблюденные данные по гидрологическим постам.
We had an observed data on hydroposts.
Кривые QH в нижних и верхних, да? В нижних и верхних веках.
Discharge level curves in upstream and downstream data.
Gauge site. И за 7 лет у нас.
Да, за многолетний период.
For the long-term period.
Суточный.
Суточный.
Yeah, that's okay. But what criteria?
До 5 сантиметров.
Уровень.
Да, уровень воды.
Уровень воды.
Да, чтобы
Water
у модели уровень.
Water level in river Kuban and branch Kuban and протока должен быть 5 сантиметров.
Не
It seemed to be no more than 5 centimeters.
How much?
На всех постах отличие уровня наблюденного от расчетного уровня должен был составлять не больше 5 сантиметров.
On every hydropost, the observed data and the actual data difference should be no more than 5 centimeters in the level values.
Okay, okay. My second question is about was about really the multi-criteria analysis, and there was a trade-offs. Yeah, and what the trade-off between what and what?
Excuse me.
Между чем и чем, вот тот самый трейд-офф. Кто конкурирует?
Конкурируют водопользователи.
Значит, есть в каждом бассейне есть набор водопользователей.
Each basin has a water user set.
Эти требования водопользователей конфликтуют между собой, как правило, практически во всех бассейнах.
These requirements are conflicting as a rule in each basin.
И необходимо выбрать такое решение, трейд-офф, компромиссное.
And there is a need to find such trade-off solution,
которое бы удовлетворяло всех.
Which will be good for everyone.
Для этого устраивается обсуждение, проводятся переговоры между всеми водопользователями.
So for this purpose, we have a conversations between all water users.
И лицо, принимающее решение,
and decision-making person
должен определить, должен сказать, что мы урезаем, не додаем воду такому-то водопользователю, такому-то водопользователю, такому-то водопользователю.
Must say which percent of water is going to each water user.
Чтобы принять такое решение, он должен видеть, сколько он теряет, если урезает одного водопользователя, другого водопользователя, третьего.
To make this solution, decision maker should see a deficit value for every water user.
Для этого мы и делаем различные сценарии расчетов.
So for this, the different calculation scenarios are made.
Это по первому по докладу по поводу Кубани.
That's about the Cuban River Basin report.
Для общего случая используется мультикритериальный анализ, который принят это на основе методов оптимизации делают.
For the other cases, the multi-criteria analysis performed by the optimization method.
Например, для сельского хозяйства мы использовали критерием это дефицит воды для оросительных систем.
For example, for agriculture, this criteria is water deficit in irrigation systems.
Для бассейна Байкала мы использовали коэффициенты, штрафные коэффициенты, которые дают нам различные варианты урезки водопользователей, недодачи воды водопользователей.
For Lake Baikal, we use penalty coefficients for
Мы
amount of
использовали
water.
штрафные коэффициенты различные для того, чтобы определить набор этих возможных компромиссов.
To determine a set of available compromises, available trade-offs.
Ну, это принятый инструментарий мультикритериального анализа.
That's the adopted tool for multi-criteria analysis.
Что вы должны сформировать множество возможных оптимальных решений, недоминируемых так называемых.
That you need to form a set of solutions.
И из них иметь инструмент, из них выбрать то, которое будет на основе переговоров удовлетворять, ну, принято будет всеми водопользователями.
And to have a tool for choosing from this set of trade-off solutions to choose one which will be good for every water user.
Это происходит на основе переговоров лица, принимающего решения, со всеми водопользователями.
That basing on the conversation between decision-making person and all water users.
А мы, группа поддержки, снабжаем различными вариантами решения и оцениваем их, и оцениваем потери от их принятия.
And we are a kind of a support group which provides our own options, and we also try to forecast the deficit values.
У нас, например, на Волге, вот наш институт участник межведомственной рабочей группы, которая обсуждает, ведет переговоры и поддерживает вот такое решение.
So our institute is a member of interdepartmental working group on Volsko-Kamsky Reservoirs Cascade in the Federal Agency of Water Resources. There's also meetings connected with water resources amount distribution between water users and
принимает решения.
And they are making decisions.
Например, завтра будет вот такое обсуждение и принятие решений, как управлять Волжско-Камским каскадом.
Decisions for controlling the Volsko-Kamsky Cascade.
И мы готовим несколько вариантов
We are preparing several options
для такого проведения
just as a support
таких переговоров.
for this conversation.
Лицо, принимающее решение, это агентство водных ресурсов.
The decision-making person is the Water Resources Agency of Russia.
И на нем присутствуют все водопользователи.
And on this meeting, there are all water users.
Энергетика, рыба,
Energy,
transport,
fisheries, navigation,
agriculture,
and
and
others.
others.
Okay, that's great. My next question was related to the violation of the violation years of the reservoirs. My question was, who actually violates the users? And if the users violate, who is in control of the water? Is it the water? Is the water authority or the users? Who violates? Because if the water is controlled by the water authority or the agency in Russia, then the users cannot violate.
После того, как на переговорах принято лицом, принимающим решение, которое у нас не является агентство водных ресурсов, после того, как принято решение, контролирует и управляет этим бассейном агентство водных ресурсов.
After the decision is adopted, it's controlled by Russian Agency of Water Resources.
А остальные, как правило, это представители разных министерств.
And others are members of different government departments.
Они следят и корректируют в случае каких-то форс-мажорных ситуаций.
They are watching and correct their values in some situations for their agricultural situation.
Но главной является агентство водных ресурсов.
But the Agency of Water Resources of Russia is the main.
Оно лицо, принимающее решение.
It's the decision-making person.
So who violates them?
Природа.
Различные, пошел быстрый паводок, ничего не сделаешь. Принято решение, что будет обычный год, а пошел быстрое половодье.
It's different nature factors. For example, the decision was made for a low water period, and then the high water period, and so on.
Professor Ragab, I would like to clarify the violation word that is being used here is with relation to the rule that has been set. That means this is not a physical violation, but this is a simulation. So it's a simulated violation. It is expected that if this particular rule is to be followed, then this particular situation reservoir will fail to follow that rule.
Yeah, but the rules.
That is a violation.
That is
the violation of the rules.
The demands. That is
The
not.
The violation of the rules. Who actually violates those rules?
No, nobody violates it because this is a simulation.
Yeah, it is simulation, but it has physical meaning.
Как правило, преимущество имеет энергетика.
As a rule, the advantage in the priorities hierarchy is for energy.
Но во время нереста имеет преимущество рыба.
But during the fish spawning period, the fisheries have priority.
Okay, so that's now the physical meaning of it.
Если я правильно понял вопрос.
Yes, if I understood.
Он спрашивал, откуда берутся нарушения. Вот кто нарушает? Нарушения происходят, как правило, из-за недостатка воды. Просто.
Или избытка.
А дальше ее или избытка. А дальше ее перераспределяют. Вот отсюда и нарушения.
Dr. Ragab, I think because this during simulation, if we are not able to fulfill the demands, then we call it either violation has occurred because we are not able to fulfill the demand, or because we can call it a deficit here. So here I think the violation is meaning the same, that the demand are not able to be met from the project. That means some violation has taken place. So that is not in the physical term. It is that it is a deficit here. Demands are not able to be met because there is some water shortage is there, or some excess demand from some sector is there which has been met because of the certain exigency. So it is like that in that case. That is my presumption from seeing the presentation and from the modeling which I used to carry out in earlier times. The simulation model using Mike Basin or even Mike 11 or Mike 21 or things like that.
We have that issue here as well, where farmers, they violate the rules by over abstracting surface water by pumping water straight from the rivers to their own reservoirs. So the rules here we have in the UK is that the Environment Agency is controlling any violation. So anyway, that's the physical meaning of it. My next question was related to the impact of climate change, especially the extreme events of flood and drought. on the reservoir reliability and operation.
На надежность водохранилища и их работу. Изменение климата и наводнений на какое влияние климата и наводнений на режим работы водохранилища.
Например, по Кубани доклад.
For example, for the Cuban River report.
Последние годы, каждый третий год стал маловодным.
Last years, every third year is lower year.
Как показывает статистический анализ.
As a statistical analysis shows.
С одной стороны, с другой стороны,
On the one hand. On the other hand,
стали очень быстро из-за таяния ледников, которые питают Кубань, стало очень быстро развиваться наводнение.
because of ice melting, there are fast temps of flooding.
И вот эти два фактора очень серьезно влияют, они все возникли в последние годы, грубо говоря, последние 30 лет.
So all these factors appeared in recent years, and this is two main factors which influence on the reservoir working.
И мы видим перераспределение приточности.
And we can see an inflow distribution.
Зимой стало больше воды,
In winter we have more water.
летом меньше воды становится.
In summer we have less water.
И становится больше экстремальных ситуаций.
And there are more extreme situations.
То есть, когда не хватает воды и когда ее много.
When the deficit of water and where lots of water.
Например, 2002 год на Кубани был самый многоводный.
For example, 2002 year on the river Cuban was with big amount of water volume. And
А 2020 на Кубани был самый сухой за все время наблюдения.
2020 on the Cuban River was the driest for the whole period of observation.
В конце июня и августа воды вообще не было. Водохранилище опустило до
В конце июля.
Давай в августе Краснодарское водохранилище опустило до
Пустое.
In the August, the Krasnodarsk reservoir was at the dead storage level because of dry.
Теперь насчет агентства водных ресурсов, которое является лицом принимающего.
Now about what resources agency, like a decision-making person.
Когда решение принято, нарушений этого решения практически не бывает.
When decision is adopted, violence in this decision is not really often.
Но это решение формируется на основе переговоров с заинтересованными водопользователями.
This decision formulated and adopted by conversation between water users.
Они не имеют права уже нарушать после того, как решение принято.
They have no rule to violate the rules after the adopted decision.
И так практически происходит.
So that's how this practically
Вот,
works.
например, на Волжско-Камском каскаде, в котором мы участвуем прямо здесь.
Okay, thank
For
you.
example, on Volжsko-Kamsky Reservoirs Cascade, when we are taking part.
Thank you. One last question by participant. It's not my question. It's a question was posted by one of the participants, and it is related to the fact that you have a high water use efficiency and inter-farm water efficiency, and it is given in a table. That value is equal to like 100% water use efficiency, or closer to 100%. So the participants was asking, how did you manage to have that high water use efficiency, especially for flood irrigation?
У нас эффективность каналов 0,65-0,75.
Нет, это у тебя коэффициент использования воды 0,86.
Коэффициент использования воды, он
бассейн.
спрашивает,
Да.
почему такой большой, близкий к единице?
Ну, потому что на орошении очень много воды идет.
Because big amount of water is needed to
На рис, там же
be
рис
on irrigation purposes. Because there are lots of rice growing areas in that territory, so
Где большой вот,
so the water consumption is very big.
Okay. I don't have more questions for you. Thank you very
Yeah,
much
thank you very much.
for your replies. Thank you.
Пожалуйста, если будут вопросы, присылайте, мы развернуто ответим на все вопросы.
And if you have any questions, please contact us by mail, which I will try to ask all your questions
Okay, thank you very much.
already. Thank you.
Thank you.
Thank you.
Okay, thank you from ICID side, Central Office Delhi. We want to thank first our president, Dr. Ragab, who was present here, who took so much interest in the presentation, and then he raised a number of questions and sought clarifications on the simulation part, because he himself is a modeler. He himself is a developer of the modeling software. So he is well aware of the things, so that he wanted to get some clarification. We thank our VTH Irina for organizing this webinar. And then we thank all the panelists for a wonderful presentation and for sharing their experience, and then modeling tools, and then modeling procedure. And we thank all the participants who were very much interested, and at maximum we were having around 116 participants at the peak time. And even now we have more than 50 participants. So we thank all the participants. Recording of this webinar will be available on our website. And Dr. Irina, some of the participants are asking for presentation. If you don't mind, you can share the presentation with us, then we can, along with the recording, we can put all the presentation on our website, so that people can go through that presentation for their reference purpose. And in the presentation, if you can add your email addresses also, then it will be easier for them to contact the concerned person through email. So in the end, we thank all the participants, Dr. Ragab, Irina, and all the panelists for this wonderful webinar. Thank you very much. Thank you all. Bye. Bye.
Thank you very much.
Thank you very much.
Bye-bye. Thank you. Bye-bye.
Bye, bye, bye.
Bye.